This is the video recording for Pre-Calculus Unit 4, Lesson 4.3. Okay, this is on geometric sequences. So if we look at the overview here, all right, geometric sequences, you can kind of relate them to arithmetic sequences in a lot of ways, and we'll talk about how those compare and how those contrast. And really, with geometric sequences, you start with a number and then you add it, you add or subtract to that number, and again, in a series, right? So a continuous pattern on and on and on. All right, now geometric sequences are going to be similar, but there's going to be some slight differences. So let's get into it and figure out what those differences are. All right, so looking at geometric sequences, first we're going to watch this video here on finding the common thread between geometric and arithmetic sequences.
Here's a different kind of sequence. What do you think comes next in this one?
Right, so it went 1, 2, 4, 8, I'm going to guess 16, right?
What do you do to come up with 16? You multiplied the previous answer by 2, because in this sequence, the pattern is to multiply one term of the sequence by 2 to find the next term. This is an example of a geometric sequence. In a geometric sequence, instead of a common difference between consecutive terms, there is a common ratio.
Okay, so again, that's one of the main differences between arithmetic and geometric. So in arithmetic, here, we might have looked at the first two numbers, okay, 1, 2, right? So then that would have given us the pattern of, oh, just add 1 every time. So the pattern should have gone 3, 4, 5, 6, 7, 8. But with geometric here, it's a ratio. All right, it's a ratio, and the ratio here was, okay, well, we're going to multiply everything by 2, right? The next number is going to be the last number multiplied by 2.
Another way to say this is that a sub n plus 1 divided by a sub n is constant for a geometric sequence. This common ratio is called R. Look at these examples of geometric sequences and try to identify the common ratio. In this sequence, the common ratio R is 5.
Okay, so again, if I can back this up here to the equation here, all right, you've got your first term, so an, right, that's the first term in the equation, and then this is n plus 1, right? So maybe if you're in the first term here, it's 1 plus 1 would be the second term. Or you could look at n being 2, so this would be 2 plus 1, right? So this just means the term in front and the term behind it. All right, and when we divide those, you get this constant ratio, which is what that R stands for. R stands for ratio.
In this sequence, the common ratio R is 1/2.
Okay, so that's what we're going to be looking for with these geometric sequences, is a repeating pattern that deals with a ratio between the number in front of it and the number behind it. All right, so looking at this here then, classifying sequences. Okay, so there's a couple things here with classifying sequences. They can either be arithmetic, geometric, or not at all. So if you look here at this first one, this is a geometric sequence. If it would go there you go. It's a geometric sequence because there is a pattern, and you're going to have to figure out what that pattern is. And if I look at it, it's multiply that number by 3. So 2 times 3 is 6. 6 times 3, 18. All right. If I look at this next one here, 1, 4, 9. Okay, that is, oh, sorry. Apologies, wrong one. So 1, 4, 9, 16, there's really no pattern. Why is it not going over there? All right, this one has no pattern, and maybe eventually, there we go. All right, this next one here, we're going to add 0.01 every time, so that makes that an arithmetic sequence. All right, if I look at this next one, 2, 4, 6, 8, right, that's adding 2 every time. All right, this one here at first might look like a sequence, but it's just dividing by the next number, and that's not what we talked about with geometric or arithmetic. All right, looking at this next one, 1, 1, 1, 1, 2, 2, like, right, there's no pattern there. Okay, something that might be not as obvious, but it is a pattern, is this one here. Okay, the 0.5, 0.2, 0.15, that's actually multiplying by a fraction every time. All right, this one here, multiplying by 4. Okay, and then this one here, we're just subtracting 3 every time. All right, so again, just picking up, picking up on some patterns here and realizing when there isn't a pattern, right? And it's okay to say that there's not a pattern, right? Sometimes there just isn't. Moving forward here, finding the explicit formula. Okay, so this is that formula or a version of that formula from the intro video. Okay, so we start with the first term and we're going to call that A1. All right, and from that term to the next term, we have to multiply by this common ratio, right? This common ratio, which is R. All right. And we talked about there, that's how we get there. But there's this new thing, this n minus 1 exponent. So the question is where might that come from, right? We've dealt with an, we've dealt with an sub, or n minus 1, and that r constant. But the question is how did we get to that exact equation? So we'll watch this here about building a formula.
If a sub 1 is the first term of a geometric sequence, then the nth term is found by using the following explicit formula. A sub n equals a sub 1 times r to the n minus 1.
Okay, again, meaning A1 is the first term in the geometric sequence. So a sub n, this equation, is the equation for us to be able to calculate any value in this geometric sequence in relation to our first term here and the ratio that we're going to figure out.
Why don't you see why this works? Begin with the following geometric sequence. You can see that the first term, a sub 1, is 3. You should also be able to tell that the ratio between consecutive terms is 2. The first term requires no multiplication. To get the second term, start with 3 and multiplying by 2 one time, or 2 to the first power. To get the third term, start with 3 and multiplying by 2 twice, or 2 to the second power. To get the fourth term, start with 3 and multiplying by 2 3 times, or 2 to the third power. Notice that each of these numbers is 1 less than each of these numbers. Now you can make a general statement. To get to the nth term of the sequence, start with a1 equals 3 and multiplying by 2 to the n minus 1 power. This same pattern works for any geometric sequence. If you know the first term, a sub 1, and the ratio between consecutive terms, r, then to find the nth term, you can use the general formula shown here. Why don't you practice? What is an explicit formula for this sequence? The first term, a sub 1, equals 1,000. The ratio between consecutive terms is 1/10. The nth term is given by a sub n equals 1,000 times 1/10 to the n minus 1 power.
Okay, so that's our general formula right there. Again, we found out our ratio because we took our second number divided by our first number, so 1/10, right? And you could do that with any of these numbers. You could divide 1 by 10 or 1/10 by 1, right? But we found our ratio here, and we plugged it into this equation. So we could figure out any number in this series based on understanding our first value is 1,000, our ratio is 1/10, and understanding what value we're looking for. So if this is our first term, this would be our fifth term. What, right? So 1, 2, 3, 4. I lied to you. That would be our sixth term. Apparently I can't count. All right, so that would be our sixth term there. Okay, so in order to calculate that, we would take 1,000 multiplied by 1/10 to the power of 6 minus 1, which gives us 5. All right, so that would be how we calculate that there. Now, moving forward here, again, that's exactly what we just said, but you might run across problems here where it's asking you to give integers or decimals. Okay, so instead of saying 1/10th, you would have to actually say 0.1. Right, 0.1. Then for the next one, it would be 0.01, okay, and then you would keep going along the line in that series. All right, so in this one here, 110, 1, 0.1, ... Okay, so a sub 1 is 100. Our r is 10 divided by 100, which is still 1/10, right? So that's 0.1. Okay, and then A5, right? If we follow the pattern here, 100, 10, 1, 0.1. This is going to be 0.01. Okay, so that would be our fifth term. All right, and then our 10th term would add a couple more zeros to that. So we would end up with 0.1, 2, 3, 4, 5, 6, right? And when we submit, there's our answers. And again, I knew this because I was multiplying it by, or if you understand how decimals work, I just move the decimal place 1 over each time. All right, if a geometric sequence begins with 8, 4, the next term looks like it's going to be 2, right? Because the ratio is expressed as a fraction is 1 over 2. All right, if for a given geometric sequence r equals 2/5 and the fourth term is 8, 1, 25ths, then the first term is, right, we would have to work backwards. Okay, we would have to work backwards and figure out if our equation is an equals a1 or a1 times by r to the power of our term, we could then work backwards. All right, now I'll leave this one for you guys to figure out so you can actually use your calculators and figure out with the fractions there. All right, now for here, how do we actually visualize what these sequences look like, right? That's been pretty much been the nature of this entire course. It's great. We understand how to do it mathematically. So what does it look like in graphically? All right. And so if we watch this video here.
Just as the graph of any arithmetic sequence in a series of disconnected points that follow a straight line, the graph of a geometric sequence will follow the path of any exponential function. For example, the graph of the sequence in the first example will look like this. In this sequence, r is greater than 1, and the graph is similar to that of a function that shows exponential growth. What shape do you think the graph of a geometric sequence will have if r is less than 1? In this geometric sequence, r equals 1/2, and the graph is similar to that of a function that shows exponential decay.
Okay, so that would be how we could visualize it, right? And obviously we're going to work later on about actually plotting the specific points and making sure that we understand how to manipulate. But in general, that's the shape of a geometric sequence. All right, so then the question becomes, how can we look at partial sums? And by partial sums, it means adding up a part of the sequence, okay? Because as it's kind of implied with the word sequence, this could go on and on and on for as many numbers as we want. But the key there is can we add up partial sums? Figuring out, okay, if I only want to look at the first 5 terms, what's that going to look like? So we'll watch this here together.
How do you find a partial sum for a geometric sequence? Since the nth term of a geometric sequence is an equals a1r to the n minus 1 power, the nth partial sum, Sn, in sigma notation, will be given in this way. This looks as if it could get complicated or tedious to calculate the partial sum, especially if n is large. Is there a formula that could help? It turns out that there is a formula. Instead of just showing it, however, let's derive it first. That way, if you happen to forget it, you can always figure it out yourself. Start with a general finite geometric series. Now, multiplying the entire equation by r. Subtract the second equation from the first, and watch what happens. Now, factor out S sub n and solve. This is the formula for a partial sum of a geometric series.
Right, and again, you can use this equation as long as you understand what the variables mean, right? Again, hopefully we can all by now plug into an equation. And again, if you need to go back and watch how we got
Subtract
there, right, this is a really, really good key here, okay? And sometimes it helps to understand how we got there in order to be able to use the equation.
Metric series.
Right? But right there is how we can calculate the partial sum for our geometric sequence, right? So our sub of whatever. So if we're saying 5 terms here, we're going to add the first term, we're going to have our ratio, and then it's going to be, you know, again, based on that 5th term there. All right. So moving forward here, All right, moving forward here, the sum of the first 10 terms of the geometric sequence is, right, we got to use that equation. All right, so we got to use that equation, and I will write it down for you so we can see that in the corner as I'm talking. All right, so let me annotate this here real quickly. All right, so there's our equation in the best that I could write it on this calculator app that I have. All right, so a sub 1 times by 1 minus r to the nth over 1 minus r. Okay, so looking forward here, all right, if that's my geometric sequence, what is the sixth partial sum of this sequence? Okay, so first off here, we'd have to figure out what the next stage in the geometric sequences, right? So it looks like I've got 2, then 10, right? So it looks like I'm multiplying by 5 every time. So this next guy here should be 50, all right? Okay, so then if I keep going, I would add up all of these. So yes, you could do 2 plus 10 plus 5, plus 50 plus 250 plus the next two values in order to get the sixth partial sum, or you could just do this value here. Okay, so what this would look like on our calculator. Okay, so what this would look like on our calculator, I'd have to pull up my calculator here, so give me a second. So looking at my equation and looking at my calculator over here, I can now do this equation. So I'm going to have a sub 1, which is my first value, so 2 times by 1 minus r to the power of n. So my r value is 5 because I do 10 divided by 2, so that's 5 to the power of, and I'm looking for the sixth partial sum, so that would be 6. Okay, then I'm going to divide by 1 minus 5. Okay, so 1 minus 5. So my value there is 7,812. So let's check it. Perfect. All right. So again, for the sake of time, I'll let you guys try these on your own here. But you're going to do the same thing. You're just going to figure out what terms you have, figure out terms you're trying to solve for, and then plug into the equation as you go. That's basically it for this unit here. So if we look over our study guide, okay, if we look over our study guide here, all right, so like arithmetic series, okay, they're connected by numbers and they're linked by multiplication or division, right? So when we're looking at those geometric sequences, it's either multiplying every number or you're going to divide by every number. Okay, if we look at this geometric sequence here, 1, 3, 9, 27, 91, okay, you're clearly multiplying by 3, so you're going to multiply 81 by 3, all right? And then that's the question. What's the common ratio? The common ratio is 3, all right? For here, you're going to figure out if it's geometric, arithmetic, or neither. So this one, since it's added by 3, is arithmetic. This one is subtracted by 2. It's arithmetic. All right. This one here, we're clearly dividing by 5 each time, so that makes that geometric. This one's multiplied by 2. That makes it geometric. And these last ones have no real pattern there that's obvious to us, so it's going to be neither. All right. And then writing the explicit formula for the following geometric sequences. Okay, so again, it is the same format every time. It's just figuring out what's the first value, okay, and then what's the ratio between them. All right, doing that here again, okay, so you're determining A1, R, A5, and A6. So again, figuring out what the terms of the values are, right, and then being able to plug that into the equation that you would have generated from above. All right, if the common ratio of the graph is greater than 1, then the graph is, the graph shows exponential growth. Okay, if it's less than 1, it's going to show exponential decay, right? And we just talked all about what exponential graphs look like. Again, kind of makes like sense that it's all in the same thing together there, eh? Okay, then looking at here for 6, the sum of the finite series is called a partial sum. All right, and in order to do the partial sum, we now have this brand new equation here, and they showed you how to derive that equation if you ever care to go back and look, right? But again, mostly it's about, can you figure out what values we have, what we're looking for, and plug them in, right? I call them plug and chug problems. Plug them into the problem and you chug through them mathematically. All right. So for example here, if we pick this one, what's the first 10 terms of the geometric sequences look like this, right? What's the sum of them? So we got 5 here, so that's enough for us to pick up on a pattern, which is multiply by 3. Okay, so that's going to be our R. Our R is our multiply by 3. Okay, our first value here is clearly a 2. And then our n term, and what's the sum of the first 10 terms? So we're just going to plug that in, and as long as you're careful with how you plug it in into your calculator, it's going to come out with the correct answer here. All right, what might get a little bit more difficult here is just fractions, and again, it's just being careful with your parentheses. So yes, this one is divided by 2 or multiplying by 1/2. So this is 1/2 to the power of 6. 6 because again, we're looking for the 6th sum term, or term sum. All right, so again, this is a really quick overview, I know, but that's because that's what this is. This is introducing us to this concept, and we'll work more with this moving forward here. All right, so then looking at our checkup here, most of these are going to be word problems here, okay? So it does seem pretty lengthy, and I'm not going to go through the whole thing with you. I just want to give you some of the highlights here, all right? So true or false, every sequence is either arithmetic or geometric, okay? The answer is false. Okay, the answer is false. It could be a lot of different things, and then there could be potential of a lot of different examples. Okay, the nth term of a geometric sequence is given by this. Write the first 5 terms of this sequence. So again, all you're going to do is you're going to carry this out, right? So you're going to start with 1. You're going to start with 1/4, and then we're multiplying by a factor of 4 every time. So 1/4 times 4 gives us 4 times 4 again, 16 times 4 again, right? And you can continue to do this, all right? And even some of the ones that might seem more difficult, like multiply by 0.1, okay? If you actually plug this into your calculator, you'll end up with these values, and you'll realize, oh, I'm just moving the decimal place, right? So again, when in doubt, use your calculator. When you feel confident, start to try to pick up on these patterns without using your calculator if possible. All right. Then saying a geometric sequence has A4 is equal to 4 and A5 is equal to 7, right? So what is A1? Okay, so you would have to work backwards. We have to figure out what the ratio is, right? Then we've got to figure out, okay, if this is A4, how do I get A3? How do I get A2? Then back it up all the way to A1, all right? Or you can do the other thing where you rewrite our original equation here. Okay, you rewrite our original equation and you solve for A1. All right? Again, whatever you are comfortable with. Okay? Now, identifying the graph as geometric, arithmetic, or neither. All right, so this one here is obviously arithmetic because it's going up by a constant number. It's a linear line. All right, this one here is geometric because it shows an exponential function. Same thing here. This is a geometric sequence. It shows a geometric decay or an exponential decay. All right, and this one here is most likely, they said most likely a radical function, right? One of those square roots. So this is neither of those two functions that we just talked about. And you can see here, the reason that is because it goes up radically and then kind of starts to slow down and taper off. So that's not either of the sequences that we talked about here. All right, then we're finding sum. So again, how to read this, S5, that means we're trying to find the sum of the first 5 terms, okay? So immediately that tells you, okay, our n value there is 5. So we're looking for whatever our ratio is, so 1/9, right? Raise that to the 5th power because that's how many we're looking for, and our A1 value is 81. So again, this is just a basic plug and chug. All right, now the ones that might be more difficult here is looking at these word problems, okay? So looking at these word problems. All right, and again, this concept check does a really, really, really good job, so I don't want to just sit here and read it to you. They do a really good job of breaking down how to answer these word choice questions, okay, these written responses. So I'm going to suggest, again, that you go through and reread this per usual, all right? But what I can tell you here, especially with these word problems, the best thing that you can do is either highlight as you go or write down the important facts that you can pull out that you know, right? So for example, it's pulling out the A value, okay, because it knows that. It's pulling out what's it worth after 3 years, right? Figuring out, okay, I've got to get to the 3-year mark, right? All of this kind of stuff, just pulling out the main information that you can. All right, and again, please read what they have as the answers and double check to make sure that you're getting the same thing here, okay?